didn't have time to cover all the problems in Homework 3 during the lecture since we got Monday, Labor Day skipped, just in case you need it before Friday because it's due on Friday. I'm going to go through some of the Homework 3 problems for you guys, okay? All right, so the first one, the problems are in parallel. If you look at the resistor network, for example, a resistor like this, you got two more resistors. It's going to ask you if, for example, labeled as R3, R4, R5 for some reason, okay? So is R3 and R4 in parallel? Actually not, because R3 is in parallel with R4 plus R5, but not R4 or not or R5. However, it's series resistors, you have to add them together, and this is in parallel with this. So none of them are in parallel in this case. So it has to be something like that, okay? Very clean. Two parallel resistors. That's one problem I'll talk about. Sorry for the noise. There's another one. Okay, so if something looks like, I can show you here. If something like this is asking you to calculate the current flowing through every branch, what you want to do is combine all these resistors. For example, current flows through here to this point, and what's happening is it's divided into or split into two branches over here and merged over here. So first we can combine these two parallel resistors into one. Okay, so R4, R5 could be just the one resistor, and you can draw it here. Then that combined resistor will be in series with this guy. Then you can do the parallel, you know, things like that. Right. Another one I'll talk about is problem looks like this. Right, so this is R1, R2, R3, R4, this is 8 volts, R5, R6, R7, okay? And it's asking you to calculate the, whatever, just solve the circuit, okay? Just solve the circuit. Equivalent resistance, for example, equivalent resistance. So you want to look at this circuit by, you know, rotating this paper a little bit by doing this, okay? Then you can start converting it. But not, since I know how to do it, so I'm not rotating the paper, so I can write down this area. So here is the power supply. You draw the power supply like this. So first you got R5, this guy, and then split into two branches. That is just in parallel, right? In parallel. And so does this go back to the cathode? No, because you have R1, R2 in front of the cathode. So you cannot directly, you know, draw it and let them go back to the cathode. So what you want to do is just directly keep going, right? So this is R6, R7, and the output over here goes to R4, and this one goes to the cathode actually. So just draw this, and there are several resistors are in. Wait, so this one goes to R4 and it's getting split. You got have R3 goes to R4, so actually R3 is here. Okay, and you have another branch has R1, R2 in series. So we have another one also goes back to cathode. Let's combine them. So this resistor here is basically R1 plus R2. Okay, so this becomes a lot easier because it's basically just two parallel resistive network in series. So what you can do is just to draw it in a nicer way, R5, right? What's a better way to do it? Oh, just to keep using the same structure. R6, R7 in parallel. So you can combine these two in one resistor, right? Just one resistor, which is R6 in parallel with R7. And then this one is another equivalent resistor, which is R1 plus R2, this guy, in parallel with R3, in parallel with R4. Okay, so in that case, you'll be able to find out all the voltages and currents and solve everything in the circuit. Right. Let's look at the next. This is another thing I want to talk about, which is another resistor network. I got 10K, I got another one here. This is A, B, 2K, 6K, 12K, 14K, 10K. Okay, so look backwards. Starting from here, the current getting split, right? Getting split into two branches, and then they merged here and come back through the to B through the 6K resistor. So what's the total resistance of this black box is gonna be 2K plus whatever here in parallel, which is 10K plus 14K in parallel with 12K, right? This is a black box, and plus 6K. That's the overall resistance of the AB. If you look into the AB ports, that's the overall resistance. Okay, let's move to the next. Let's see. A, B, this guy, here, 300, 250, 150, and 200, and 600, like that. So what's the resistance if you look from these two ports? Okay, so basically you start from one point. For example, you run a current through here, it's getting split into two branches. So when it arrives at this point, you got two parallel resistors, and here you got a series resistor and a parallel resistor. So what's happening is you have A here, you run a current through it, you see the first time it getting split into two. So you are getting one parallel resistor, which is 200 in parallel with 600, right? And then keeps going to the other direction, and you are getting another resistor. So they both go back or come back to the port B. So this one will be the equivalent resistance of this part. If you're looking from the top, let's just keep consistent, right? So it's always looking from the top. And then you have this one to be 300 in parallel with 250 plus 150. Okay, that's the resistance of this guy. Next one. So this one has a power supply, one resistor, two resistors, and here's the output. Doesn't matter where it's defined as the output. If you know the voltage, you know the current, you know the resistance, you should be able to find out V out, right? So this is 4.7 kilo ohms, and this is 3.3 K ohms. So you use the voltage divider theory. For example, we ground it here, as we derived in the class today. So V out will be 160 times the resistance. The resistance ratio is the same as the voltage ratio, right? So this one takes a 3.3 K ohms share of the overall resistance. So just directly write it down. So 3.3k ohms over 4.7k plus 3.3k. That's it. And the second question is trickier, or the third question, doesn't matter which one. It's asking you about the R1 minimum or R2, well, and R2 minimum if the power max or the power readings of the resistors are like 1.0 watts. You know, this is a power reading of the resistor. It cannot handle anything higher than 1 watt. So this is what you have to know. But same circuit, same voltages. So through this calculation, you can find out V out, and then you use 100 volts minus V out, you can get V1. So you will be able to know the voltages here and the voltage here as well. So it's telling you that the voltages are not changing because the no load. So what does that mean? The no load voltage. No load voltage. It's a new term here. So no load means at the output there's no load. Like sometimes you got a resistive load, capacitive load. No, nothing. It's an open circuit. Okay, it's just measuring the voltage across R2. So there's nothing, no load. So it's basically just a load across R2. Okay. So it's telling you that the no load voltage is not changing. So the voltage here is not changing because this is the voltage source is not changing. So if this voltage doesn't change, the voltage across this resistor will be the same. Okay. So given that, we could do something in order to find out the minimum resistance that we can use for the circuit. So for example, we know V1 is like X volts and V2 is Y volts, okay? And definitely V1 plus V2, which is X plus Y, which is 160 volts. So you can definitely calculate it. I don't want to directly give you that solution here. So we know that the power of the resistors are P equals IB equals I square R equals V square over R, because now we have V's are constants and P is given, sort of given, is maximum 1 watt. Let's assume that R1 is taking that entire 1 watt power. Okay, so we are just assuming, okay, because there are just the two cases. This is case 1. R1 minimum is V1 square over power, right? Power max, which is 1 watt. Let's assume R1 is taking all of the 1 watt rating. So V1 is actually X, right? So the X square, which is calculated, I'm just showing a variable here. So X square over 1 watt, which is basically X square ohms. Okay, so in that case, you will be able to calculate I, the current. So I will be, it's just a very simple circuit. Then you calculate I, which is V1 over this X, right? X square, right? X square, which is this resistance we just calculated. And since V1 is given, it's not changing. So eventually you can find a current, okay? And in that case, you will be able to find out R2 as well, because R2 in this case will be voltage divided by the current, will be V2 divided by the current we just calculated. Okay, so in that case we can find R1, R2s. That's case 1. So for case 2, you assume that R2 is taking all the 1 watt power. because you don't know which one is going to take that 1 watt. It's unlikely that both of them are reaching the current or the power rating at the same time. So assume the case 2, R2 is taking that entire 1 watt power and goes through the same thing to calculate R1. So are getting R1, R2s in this case as well. So eventually you have 2 sets of R1 and R2s. And because that the voltage doesn't change, which means the voltage ratios doesn't change. You can compare which is taking more voltage. It's just a 1 voltage divider. If the one is taking more voltage, it must be a higher resistance. So if you come back to this calculation, you got 2 sets of R1, R2s. There must be just one of them satisfies this condition. So, you know, it's given. The voltages are not changing, right? Find out the bigger voltage, the resistor with the bigger voltage, and it has to be a bigger resistance. You come back to the calculation. If the resistance of that resistor is not bigger, you have to switch to the other one. Okay, I couldn't tell you more, but I believe you will be able to sort this out. It's not too difficult. And the last one is a little trickier. We have to talk about it. Right, so which is this guy? It's telling you that this is a bridge circuit, Wheatstone bridge, but actually the resistors are not making sense to the bridge circuit. Anyway, it's just a circuit 1 problem. Let's just solve it. It's telling you that the I across this sensor, across this detector is ID. It's called ID, and here's node A, B, C, and D. Okay, it's telling that VBC, the voltage, is very close to 0. You can ignore it. It's interesting because there's no voltage, but there's a current running through it. Because the sensor is very sensitive, the voltage difference is tiny. However, there's a tiny current flow through the sensor and allows you to detect it using a very high precision ADC. But this is not something we are working with in this case. Let's just find a way to calculate it. So I think it's asking you to calculate ID, right? So because these two the voltage difference between these two nodes are no difference, is 0, right? So in that case, you can directly merge. You can consider these two nodes are just a 1 node. So you're getting something like this, A here, right? And you have 1 resistor, and you directly short it. I don't know if this is helping, but let's keep drawing and see how that goes. 15K, 3K, and 9K, and 45K. So yeah, let me redraw it. It should be this. Like this, and then like that. Okay, so this is 15K, 3K, 45K, and 9K. Same voltage, so we can get a parallel resistance over here, parallel resistance over here as well. A, B, and the voltage across AB or VAB, VAD is VS. This is given. Okay, so in that case, we can calculate the voltage of this main of these 2 parallel resistors, and then these 2 parallel resistors. So which is, well, the current, actually the total current, I equals Vs over, right? So I got a parallel resistance over here, which is 15K times 3K over 15K plus 3K. That's this resistor, and plus this resistance, 9K times 45K over 9K plus 45K. So that's the overall current. If you get an overall current, you will be able to find out resistance or the voltage dropped across this thing. So which is the current times this parallel resistance, which is 15K plus, times 3K over 15K plus 3K. So that will be the let's label it as V1. So this is V1 and this is V2. Okay, so V2 will be current times, because the main current flows through this black box equals the current flows through this black box, right? So the current flows through this black box times the equivalent resistance of the parallel resistor, which is 9K times 45K over 9K plus 45K. So this will be V2, the voltage dropped across this box. The V1 is the voltage dropped across this box. So in that case, we can, since we know the voltage, right? We know the voltage. Oh, I don't need another paper actually. I'll just draw it here. So you know the voltage across it, and you know the resistance of every single one. So you will be able to calculate the current here. I1, let's say. Okay, I1 can be calculated because you know the voltage, you know the resistance. You can calculate the current. Same here. You got a V2, which is the voltage across the parallel resistors, which is also the voltage across 9K. So you can calculate I2. If you look at this circuit, which is the original one, similar to this one, you calculate I1 here, you got I2 here, all right? So it's not difficult to find I here. This is ID, right? Just use this one minus this one, according to KCL. Okay, hope this helps.